Hey everyone, and a very warm welcome to KognitoKey. Today, we're jumping into a topic that is absolutely crucial for anyone studying digital electronics, the Karnaugh Map. Trust me, if you've ever stared at a super long and confusing logical expression, this little visual tool is about to become your new best friend.
So, here's our game plan for today. First, we'll talk about why we even need something like a K-map. Then, we'll get into what it actually is and cover the basic rules. After that, we'll roll up our sleeves and solve a three-variable map together, step by step. And finally, we'll level up with some more advanced tricks. Sound good?
So let's start with the big question. Why bother simplifying anything? Well, in the world of digital circuits, every little piece of logic translates to actual physical hardware, gates and wires. The more complicated your logic, the more hardware you need. And that means higher costs, more power usage, and a slower circuit. The goal is always to get the job done in the simplest way possible.
I mean, just look at this thing. Imagine your professor gives you this massive Boolean expression and tells you to simplify it using just algebra. It would take forever, right? And it's so easy to make one tiny mistake that messes up the whole result. There just has to be a better way.
And lucky for us there is. This is where our hero of the day comes in. The Karnaugh Map, or as we all call it, the K-map. It's a really clever method that basically turns all that messy algebra into a simple, visual puzzle.
So, what is it really? A K-map is basically a truth table that's been cleverly rearranged into a grid. This special arrangement lets us use our eyes to spot patterns and find redundancies. It lets us simplify things without having to fight with all those complicated equations.
And the size of this grid or map depends directly on how many variables you have. The formula is super simple. It's just 2 to the power of n. So if you have 2 variables, that's 2 squared, which gives you 4 cells. For 3 variables, you get 8 cells. And for 4 variables, you get a 16-cell grid. It's set up this way so that every single possible input combination has its own little box on the map.
Okay, now for the fun part, learning the rules of the puzzle. Before we can start solving, we have to understand the layout of our K-map board. But don't worry, once you get these few key rules down, everything else just clicks into place.
Here are the big ones. First, and this is the most important rule of all, only one variable is allowed to change between any 2 cells that are next to each other. Second, when you start making groups, think big. You always want to look for the biggest possible groups of ones first, groups of 8 or 4 or 2. Third, you can only group horizontally or vertically, no diagonals allowed. And finally, for now, we'll be placing 1s on our map to show which output should be true.
Now this slide right here, this shows the secret sauce behind that one change rule. If we use normal binary counting, on the left, you can see that going from 01 to 10 changes both bits. That would break our system. So K-maps use something special called gray code on the right. Just look at it. As you go down the list, only a single bit flips at a time. That little trick is the magic that makes this whole visual grouping thing work.
All right, enough theory. Let's get our hands dirty and actually solve something. We'll walk through a 3-variable map example step by step.
Okay, here it is, our puzzle board for 3 variables, A, B, and C. It has 2 to the power of 3, so 8 cells in total. We've put variable A along the side for the rows, and B and C across the top for the columns. And hey, look at those column labels, 0, 0, 0, 1, 1, 1, 1, 0. There's our gray code in action.
Now let's plot a function. This function is true for the minterms 0, 1, 2, 4, and 7. So we just find the box that corresponds to each of those numbers and put a 1 in it. For example, minterm 0 is where A, B, and C are all 0. On our map, that's row 0 and column 0, 0. So we pop a 1 right there. What about minterm 7? That's where A, B, and C are all 1. That would be row 1, column 1, 1. We just do this for all the minterms in our function.
Okay, now for the grouping. We're looking for 1s that are next to each other, and we circle them in the largest possible groups. See here? We can circle a pair of 1s for minterms 0 and 1. We can also group 0 and 4 vertically. And notice how that 1 in the corner is now part of 2 groups? That's totally fine. Our goal is to make sure every 1 is in a group. We also have a pair for 0 and 2. And poor old minterm 7 is all by itself, so it just forms a group of 1.
So how do we get our final answer from all these circles? It's pretty cool. We look at each group one by one. For that first group with minterms 0 and 1, notice that A is always 0 and B is always 0. But C? C changes from 0 to 1. The variable that changes is the one we eliminate, so C is gone. and that group gives us the term A bar B bar. We do this for all our groups, and then we just OR them together. See? So much cleaner than algebra.
So now that you've got the basics down, are you ready to level up? The same ideas apply to more complex problems, but now we'll look at a bigger 4-variable map and a very powerful trick called don't care conditions.
Here we go, a 16-cell map for 4 variables, A, B, C, and D. It's bigger, but the rules are exactly the same. Notice we have gray code for the rows, labeled AB, and for the columns, labeled CD. And just like before, we take our function and we place a 1 in the box for each min term.
And this is where bigger maps get really fun. With more cells, you can make bigger groups. In this example, we can circle a quad. That's a group of 4 ones. And quads are great because they eliminate 2 variables, which makes our final answer even simpler. We also find a pair here, and look at this, another pair that wraps around from the right edge all the way to the left. You have to imagine the map is like a cylinder. It's continuous.
Now, for that special trick I mentioned. In some circuits, there are input combinations that should never, ever happen, so we don't care what the output is for them. We mark these with a D or an X. And the beauty of a don't care is that it's a wild card. We can pretend it's a 1 if it helps us make a bigger group, or we can just ignore it if it doesn't. It's a free choice. Let's see this in action. Here's a function that has both our regular ones, the min terms, and some D's, our don't cares. We plot them all on the map exactly where the function tells us to.
Now watch the magic happen. If we only had the ones, we'd be stuck making a bunch of smaller groups. But look what happens when we use those D's. We can use the don't cares in that first column to help us form a big quad of 4. And we can use the ones in the second row to form another large quad. By strategically using these don't cares, we've made much bigger groups, which means a much, much simpler final answer.
And here's the final result. By taking advantage of those don't cares, we've managed to boil that entire function down to just 2 simple terms. And that's not just neat, it's practical. Fewer terms means fewer logic gates in the real circuit, which makes it cheaper, faster, and more efficient. That's the real power of the K-map.
So, to sum it all up, K-maps aren't just some abstract thing you learn in a textbook. They are a genuinely powerful, practical, visual tool that engineers use all the time to turn complicated requirements into simple and efficient digital circuits.
And that brings me to a final thought for you. The K-map is such a brilliant way to see the solution to a problem in logic. It got me thinking, what other visual tools, charts, or maps have you come across, maybe in other fields of engineering or science, that do the same thing, make really complex problems feel simple?
And that's a wrap on our K-map explainer. If you found this helpful and it made things click for you, please do me a quick favor and hit that like button, share it with others who might find it useful, and of course, subscribe to KognitoKey for more explainers just like this one. Thank you so much for watching.